Good evening, everyone. This is Vishwanath and Pranav. So, we are presenting our data mining project on optimizing cache replacement policy with block prefetching. Now, before we go into all these complex terms, let's understand what is caching. Caching is the process of serving data requests from a fast cache, which is a memory solid state drive rather than a comparatively slower device. So what happens is that when you're requesting for a data, if the data is present in the cache, it is recorded as a cache hit and we return the data. If it is not present in the cache, then it is recorded as a cache miss and you read from the storage and return it. But when do you cache is that the smallest unit of data which you can cache is called a block. So when there is a miss, then you take the block of data from the storage, return to the user while storing it in the intermediate cache as well. So in this, a very important concept is called temporal locality, where it records the blocks that have been recently used are more likely to be accessed again. Now, how do you cache? Is that how do you select the blocks to maximize the cache hits? It can't just be random. So we use multiple replacement policies such as least recently used, most recently used, first in, first out, and least frequently used. But what do you mean by cache prefetching? When you want to prefetch something, it means that you are getting it before it is being requested. Similarly, in a cache, before a request for a data comes, we are loading the data into the cache. Now, based on historical data, it can be sequential, or based on block association, it can be blocks that are frequently accessed together, or if it is, it can also be spatial locality where a block is accessed, then it is likely the adjacent block to it will be accessed as well. Now, going forward, Pranav would take over.
Okay, so now that Vishwanath has presented the problem, so I will talk about the data mining approach to this problem. So as you know, we are trying to prefetch data before it is accessed. Therefore, we're looking to mine different block access patterns. Specifically here, we're looking at block associations. We want answers like if block A is accessed, it is highly likely that block X will be accessed soon. And in that way, when A is accessed, we can prefetch block X expecting a request soon. So the data that we have are traces from data center systems, and we have the time for each request and the location. And we have other information, but they are not relevant to us. So we use sporadic association rule mining in order to get block associations, which we use to prefetch data. First, what we get is the frequent item sets that are the blocks that are usually accessed together, and then use association rule mining in order to discover relationships. So we try to identify the mid-frequency items. It is because the high-frequency items will be already handled by the cache because they're requested so much, and low-frequency items do not need to be in the cache. So usually the cache misses result from items that are mid-frequency. So therefore we filter request during the item set filtering process. So the three main process is generate the item set, filter the item set, and just leave the mid-frequency items, and then use association rule mining to generate associations between these different blocks. So our experiment comprises of taking a trace, splitting them into train and test data, using the train data, running sporadic association rule mining to get the association table, based on which we prefetch data during the cache simulation we run on our test data. So we use a cache analysis framework called C-memory cache, and the two main evaluations are how much data should I collect, because it is a main source of overhead, and how to manage the prefetch data, because usually we have the notion that the replacement policy for the main cache and prefetch cache should be the same. So as we can see, that increasing the training data set size doesn't necessarily improve the performance. Therefore, when we're designing systems like this with prefetching, we need to investigate what is the right size of the training data. Also, as we can see here, the hit rate of the 30% of W93, where only 30% of data was used as training, is the highest. So it doesn't necessarily mean that adding more training data always improves. So we look here at the replacement policies for one of the workload, 93. We evaluate different replacement policies and see the hit rate, and we can see that MRU replacement policies works the best. Although the main cache might be LRU, the prefetch cache can be MRU. The same case in W99. And whereas another workload we evaluated, LRU came out to be the best. But what we can see here is that the replacement policy performance in the prefetch cache can be different from the main cache. So in order to conclude, the two findings from our project has been that increasing the training data set size might add more noise to our prefetch data, and also that the same replacement policy doesn't necessarily should be used for cache and the prefetch cache. Thank you.